like the most people like elementary math class.
I love it. I love it. Yeah.
I don't know, but we got a surge of genius or something.
Thankfully,
Yeah.
you know, it would kind of suck if I were you and you came in here and I was teaching you like you were an elementary kid. I would think you would be a little like, wait a minute, I know some shit. What are you doing to me? So obviously, we're going to do this stuff. And part of the stuff we do is, like we said, so you can kind of relate to how they feel, right? You learned your addition. If I teach you addition, you're not going to feel the same way they are because they don't know what the hell this sign means. Holy shit,
Yeah.
right? And part of it is just so that we more deeply understand a concept ourselves. So I like the idea that in order to teach a subject, you really should know like a few classes ahead of that material so you can give it a more roundabout, like a more well-rounded discussion. Right? I don't want to have an algebra teacher who's only ever taken up to that class. That would so suck. Okay. Are you working? Not too good. Hold on. So, if you write down the places, there we go, look at you guys. That's right, just take a break there, back. 25, 5, 1 decimal, 1/5, 1/25. Now look at 0.24. What does 0.2 mean? And because of course, this is in base 10. So what does 0.2 mean? 2/10. So that's 2/10. And what does 0.04 mean? 400. Now look at what's really cool here. 2/10 reduces to be 1/5. So I need 1/5. 400 reduces to be 1/25. So I need 1/125. So if you do 1/5 plus 1/25, you will get 2400. You get 0.24. Isn't that neat? It's not that bad, right? It really, well, okay, this problem is not that bad. You could probably understand that decimals don't really convert that easily between things. I picked a problem that was relatively easy, but it was still hard because you had never seen it done before. I just wanted to see who could kind of tease out what the next step would be. Okay. Anything else from that test? Anything else freaky?
Could you just go over the bonus number 2 question?
Oh, the beat. So that one was sort of a brute force problem because you really did have to write out, you have to figure out what T means. A is 10, B is 11. So if I were one of you guys, I'd be like, all right, oh, no. Because that's going to just take a while. So that's really for the person that just flew through the test and now you got this thing you can sit there and do for a while to figure out what T is, right? You guys with me?
Yep.
Now there's a way you could start at Z and work back to figure out what T is, but I mean, that's up to you. The funny thing is, A through Z, would that be enough digits for base 40? No. Why does it not matter? Because I only gave you letters from our alphabet, so it doesn't matter what the other symbols would be. But that's all you got to do. What T is in what base? In what place?
29.
Say?
29.
Oh, no.
Oh.
Sorry. T would represent 29. What place is T in the number? The ones. What about that E? That first E there. Work it this way. 40s. 1600.
64.
All right, good. So you got B is 11. So you got 11 64,000s plus, works exactly the same way, just bigger numbers, right?
Yeah.
So you could have base 7,283. You can have that all day long. The pattern, the method you do doesn't change. It doesn't change. Just bigger freaking numbers. And obviously more symbols required. Base 7,823 would require that many symbols if you include 0, right? So, okay, how you guys doing? Everybody? All right. Some of you guys just look a little down. I'm sorry. I'm in math class, so I'm down. Okay. So, anything from homework or anything else from the test? That was awesome. Did you just realize something? Is that what happened?
Yeah, I was like, what did I do? But now I see it.
Yeah, let me know if you have a question, if you're not sure why I took some points off, or you need a nudge in the right direction.
Yeah. It was this one, you put a question mark for what, was I missing one?
Yes, you're missing at least one, which this was kind of weird to me, because this is where the thing you're missing would go.
Oh, I didn't think it was, like, I did put it there originally, but then I
Because
crossed it out.
or means everything in A should be in there, and you're just adding stuff to not be. So if you see something in A that's not here? Yeah.
I did a general question.
Is that number B?
We get a question what you said.
Number B.
Same.
Of the-
Yeah, everything
That was-
you can
I
correct.
did it and I was like,
Yeah.
So guys,
Took
you
out
can correct
D.
everything in this class once, right? Except for the final. And I always have some students like, oh, can I just come to your office? I can look at the final. We can. No, final's final. So, but everything else you can correct once. I like it. So please don't resubmit. You turn in corrections. I give it back to you. That transaction is done. Don't do a second draft. This is not English class. Okay. Anything else from homework or yes? Which one? Yeah. Oh, yeah. So I try to make it understood that the book uses the letters T and E, remember that? And I just said it's better just to in general use A, B, C, D, because then it's automatically good for whatever base. So there was a problem 2A9, right, that one?
Yeah.
What does A mean? So it goes 0, 1, 2, 8, 9, and I can't write 10 because that's 2 places, but I'm in base 12. So I should be able to go up to 11. Just like in 10, base 10, I go up to 9, right? I have a single digit for every number up to 9 in base 10. Because base 10, this is the tens place. So I just need to go over here. One more would make that roll over to 1, and that would roll over to 0. So I need a single digit for 10 and a single digit for 11. And what we chose is to use the letters A, B. A is 10. That's what I'm saying now, what we said earlier. Yes. So because watch this. If I did this, how many places are here? 3. And that's the 1s, that's the 12s, and that's the 12 times 12s. If I wrote this because I wanted a 10, I'm screwed because now there's 4 places, and that's a completely different number now, right? Okay, good. That's why I need a single digit for the number 10 if the base is bigger than 10. And so we just chose, we could have used a happy face and a sad face or whatever, but that would get a little crazy. Okay. Because again, just to remind you, the symbol we use for 2, for example, is arbitrary to a certain degree. Somebody back in history said, well, when you use something that looks like that, right? Everybody's like, that's cool, and this one guy in the back was like, I don't like that, so they killed him. And, things were a little bit more brutal back then, so. We like the simple die. So, nowadays, we don't do that as much, or ever, or very few people get hurt in my class. Okay.
there's a thing about like angles.
Yeah, that's kind of dumb. It's not real. Yeah, somebody trying to make something up to make something make sense. It's not real.
Fill out in the book.
Yeah. That was not a true theory. It's just sort of like somebody was trying to make something that sounded good. I kind of like the idea. It's kind of a neat idea in itself, but it's nothing connected to any of it. Yeah. All right, guys. All right. So, there's some more questions from the test. Homework, we're going to get into chapter 3. And chapter 3 is where we learn how to add and subtract. Where's the little dude? Let's see if you bug me. Oh yeah, get out of here. So, I'm gonna do some lecture. We're gonna watch some nifty videos. We'll see if we have any old favorite show, the young peoples. See if we have any favorites to show up. So we kind of working our way up. So we introduced the idea of let me try to say this right. Natural numbers. 1, 2, 3, 4, 5. And whole numbers really, because we had 0 in there also. We're not talking about integers yet. And what's up with integers? What's the thing with integers? What do they introduce? Does anyone remember? Not decimals, that's rational. Negatives. So integers introduce the idea of negatives. We're not there yet. So it's kind of funny to me is we're going to talk about addition and subtraction right now, but we're not allowed to use negative numbers or have negative results. And there was a time in history, I might show you this cool little video at the end of today's class, if I remember, where they talk about, the thrust of it is really imaginary numbers. Have you guys ever heard of imaginary numbers? When we first came up with the idea of negative numbers, people thought those were imaginary. So they rebelled against them, and then they started to realize, oh, they have a use, right? Because what does 2 apples minus 3 apples equals negative apple mean? What does that mean? So like a little apple black hole, right? Apple black hole pie. No, it's bad. Don't do it. Don't go close. But we know, some of you guys know this all too well. When I was in college, my bank told me negative numbers existed all the damn time, right? And then they're like, oh, you're the negative. We're going to take money from you even though you have negative money. Oh, thanks, bank. You're so nice. Right. So you guys know what I'm talking about. One model for addition is the set model. Jeff, 3 letters. There you go, buddy. I misspelled the word set. That's awesome. The set model of addition, which is kind of like, this is almost following an evolutionary track, right? We have to have some concept of this idea of adding things. And the most basic way to think of adding things is, I got 3 rocks. This other caveman came over and dropped 2 rocks. Now I got 5 rocks, all right. Right, so this idea of actual sets of physical items. So this set represents what number? 3. I like it. It's amazing. And if I have another set, what do you got, Jeff? It doesn't matter. Just draw. There you go. There. No, you've already got it. Let's draw. There you go. Star and a square. I like it. Thank you. I'm open to suggestions. So if I combine these 2 sets, if I just pour them in the same cup or whatever, I'm looking like these are 2 cups I'm looking down from above, and I just pour them in the same cup, obviously how does this capture the idea of addition? How many things are in this set? So let's call this set A, we'll call this set B, we'll call this set C. Do you guys remember how to represent the number of things in set A? I don't know if anybody remembers that notation we use. It was kind of like exactly what you would want. The number of things in set A. So the number of things in set A plus the number of things in set B equals the number of things in set C if A and B have no intersection. Okay, so that's getting a little bit extra there. Hopefully that kind of makes sense. Right, if these were 3 things and I put the circle here, the circle's already there. Okay, so maybe. Now to be really, really honest, and this is getting a little bit weedy. If I had in this cup a triangle, a circle, and a little spiral thing, and I had in this cup a star and a circle, aren't those 2 different circles? So I kind of disagree with the book a little bit here, but you know. All right, that is taking an idea like adding two numbers and just going deep. Okay, but this is the set model. And a lot of times, this isn't what you're going to teach. You're not going to teach your students this, yes? You're not going to teach your students this shit. You're going to be working with them on this level, where they know how to count things. They know how to count things. You pour them in the same cup, and you say, okay, count how many you've got now. Oh, what is 3 plus 2 then? Right? And they're like 4 because they ate one of the things. No, don't let them do that. Okay. So that's the set model. Do you want to get this specific? Maybe. No, I'm not going to get that. So yeah, so if I have A plus B, this is, what's the official name of this? This is kind of a weird question. That's adding, but what's kind of like the official name for addition? Sort of like multiplying is product, subtracting is difference, adding is sum. I love it. So here, you want to really get freaky. What are the parts called? What are the parts of a sum called? Some really weird words you don't ever see.
Agents.
I love it. They are called addends or summands. With a freaky looking M. I'm not going to use those words much. Nobody really does, ever. But they're there. Those are what they are officially called. And again, you're not going to talk to your little, 5-year-old and say, these are the summands. No. Okay. Now, let me ask you something. If I said, let me show you an example. And just go with me. This is simple, but I want you to notice something. If I said, what is 8 plus 11 plus 9?
Great.
How did you do that? What did you do exactly?
I added 11 and 9 because I know that.
Good. I love it. So this is going to be something we talk about in a bit, is adding strategies. So you look for the round kind of numbers, right? Do you think beyond something like 1 plus 1 plus 1, which is, right? Anything more than that, you can only really do 2 at a time, yes? I would be surprised as all hell if somebody could do 13 plus 47 plus 63 all at once. Think about it. That's basically impossible. So addition is something we call a binary operation, right? You have to do 2 things at a time. Okay, so addition is called a binary operation. It only operates on 2 things at a time. Okay. Now, another model that has a lot of uses past just this. It's a way that you'll teach subtraction. You start talking about 2 things subtracting, make a negative number, all that kind of stuff, but we obviously can't be there yet. But it's it's called the measurement model. And in this instance, the measurement would be on a number line. So if I said represent 2 plus 3 on the number line, how would you do that?
Do like your little hops.
Yeah, dude. So you can start at 2, right? You got to start somewhere, start at 2. And then you want to add 3. It's crazy, right?
Yeah.
So now it's becoming an idea of motion, right? So you have the physical stuff you can give them, and they can start counting them and putting them together and counting them, right? But this is just one little step up from that. This is a more conceptual idea. It's an idea of movement. And we all know this kind of thing, right? We all know if we add, we go to the right. If we subtract, we go to the left. Okay. So it's a beautiful, whole other way to consider addition, subtraction. Okay. Very basic. We all know how to do this shit, but it's from their perspective, it's a complete shift of what they're working with and how they're looking at it. Okay. So, let me see. Yeah, we'll do more of that in a minute when we get to subtraction. I like it. So here comes a, well, let me see if you guys know this. This first one you might not know. So let's talk about the properties of adding whole numbers. Later we'll extend them to all numbers, but the first property might be one that not everybody's heard of. You guys have heard of such properties as commutative property, associative property. Okay, they're coming. The first one is called closure. So it's when two numbers break up and they don't, no. I just need closure, no. Closure is if I add two whole numbers, what does my answer have to be? Can it be a decimal?
No.
If I add two whole numbers, my answer has to be a whole number. Do you see how that means it's closed? So if I subtract two whole numbers, does the answer have to be a whole number? No. What's 5 minus 7? -2, not a whole number. That's an integer, right? So are whole numbers closed under addition? Yes. You cannot come up with any two whole numbers that add to be something that's not a whole number. You can't. Is it closed under subtraction? No, because two elements of whole numbers could subtract to be something in a different set, something an integer. Does that make sense? So that kind of is cool. It's kind of like if you start in the whole numbers and you do this thing, you end in the whole numbers. You're closed. Where if I subtract, I could have two elements here. 2 minus 5 is now over here in the integer. Oh, shit. It's not closed because they left. I don't know how you guys feel about it. I've always liked that word closed, closure. Right? They stay within itself. It doesn't go somewhere else. Okay. I'm not sure to capture that. The whole talk here, but whole number plus whole number. Equals whole number. Okay, that's what that says, because I know you can't read. Okay, let's just keep going. Anybody remember what the hell this is? And if you can spell it right, Jeff. Commutativity. Does that sound right? Sounds right to me. Commutativity, there it is. Jiminy Jeebus. Commutative. Commutativity. Anybody remember what the hell that was? You know, like we knew the word, dude.
Willing to take the bus?
Huh? Yeah, you commute. Yeah, it's kind of funny you say that because that's exactly how I teach this. Right? Commute. If you have a commute, you start somewhere, you go somewhere else, right? So commutativity is if I have like 7 plus 8. Is it the same thing if I commute? If I make the 8 go here and the 7 go there, is it the same answer?
Yeah.
Yes. Since that's the same answer, addition is commutative. Notice there's no N in that word, right? It's not, we don't want to live in a commune. It's not communitivity. It's commutative.
There's like a saying that's like the order of the factors doesn't alter the product.
Say again?
The order of the factors doesn't alter the
Oh,
product.
yeah. So we'll get there when we do multiplication.
That's multiplication.
Yeah. So we'll talk about that. I love it though. It's the same idea. So multiplication happens to also be commutative because 8 times 4 is the same thing as 4 times 8. And then you talk about the factors.
Yeah.
I love it. Is subtraction commutative?
No.
Hell no, because 7 minus 8 is not the same thing as 8 minus 7. I like it. All right. Not too bad. What about associativity? Associative property. Oh crap. Anyone have any recollection of anything about that? Besides, sounds like somebody's got to tell somebody else off. You associative person. So, associativity is a lot like commutativity, it just adds one extra layer. So 4 plus 3 plus 5. So with commutativity, individuals commute. So if I have individual numbers and they change places or they move around, that's commutative. Parentheses, associate. So is this true? What's the only thing that moved there? Now be careful, is that true? Try it. Does it matter if I have a long list of things I have to add? Does it matter what order I add them in? That's all these two things really say. They just say it in specific ways. This one says you can take any number and move it somewhere else in the addition. It's the same answer at the end. This one says you can, and this is what somebody did earlier when you were like, I added, I can't remember what it was, 11 and 29, whatever it was, to make a whole number. Because you know you can add whatever order you want to, right? So of course this is 7 plus 5 is 12. This is 4 plus 8 is 12. Same elements, so the sum has to be the same. Is that all right? You guys okay? Some guys look at me like, I'm going to prove you wrong. Do it. Prove me wrong, please. Please prove me wrong. That'd be the coolest day of my life. Prove me wrong. That'd be so awesome. Okay. And then the last one for now, identity. Sounds like we just started a psychology class now, but no. In closure, we have identity. Or it could be a study of that John Cusack movie. Anybody ever seen that? No? Okay, sorry. It's a really cool John Cusack movie. All right, has anyone heard of identity property in, yes? Do you remember what it was? No? Okay.
Like a 9 will be a 9 or?
Yes, so, but it involves addition. So go with that. What do I add to any number and it stays the same? Its identity doesn't change.
0.
0. So 0 is the additive identity. Good Lord, I'm writing really well today. 0 is the additive identity because any whole number plus 0 is the same thing. It stays the same. It doesn't change. And isn't that exciting? Ground shaking. Now what I want you to understand real quick, this seems kind of silly, but the idea of identity becomes more important when you start talking about other number systems or other ways to do this whole thing. And that gets really trippy. We're not going to do that right now. But we could have had an entirely different set of mathematics. The identity could have been 7. We could have set it up all differently, but that's not how it is. The identity is 0. Okay. What would be the multiplicative identity? 1. That's what you multiply by to not change something. I love it. Kick ass. So the same idea, just different answers for different operations.
So then for subtraction, the identity would also be 0.
That's a little bit hairy because it's also has to work the other way. So like a minus 0 is still a, but 0 minus a is now negative a. Oh shit. So it doesn't really work for subtraction and division because of the non-commutativity. Yeah.
They're like the bizarro.
Yeah, the mirror world. All right. So those, the middle two definitely you guys have heard of before. Right, the first one hopefully is pretty clear, and the last one should be really clear. Okay. Now where things get really interesting. So, let me see, do I want to, yeah, why not? Everybody got this here? Okay. So we're not talking about multiplication, so I'm not going to make a multiplication table. I am going to make an addition table. Why are you holding it like that? I don't know. I learned that I didn't make the dimensions well enough. Let's see if I can do this. Almost. So I'm going to start with like 0 plus 0 is 0, for example. Okay. Right? But there's a major thing to realize right off the bat. One of the properties cuts this in half in terms of what I have to kind of learn. So, whatever 1 plus 7 is, isn't that the same thing as 7 plus 1? Because that's what commutativity means. So I can kind of cut this thing in half. I should just do it out of the book, because I'm going to mess this up. Yeah, see, I already messed up, sure. Let me show you this in the book. Me trying to draw it, that's kind of a nightmare. It gets cut in half because anything I fill in on the first part is going to be repeated in the second part. So it's less stuff to memorize because of the property that we know. So let me just show you this real quick. Well, this would be good. This is a transition right into the videos. I'll pretend like I meant to do this. So, I meant to do this, it's all good. Today's lecture is sponsored by Panasonic. This is page 91. So this is what I was worried about. I wasn't exactly sure where the hell to put that line. But basically, not quite half of it, but this part of it is, so whatever 1 plus 2 is, 2 plus 1 will also be the same thing. So the minute we learn 1 plus 2, we know 2 plus 1. So what we want to do is we want to try to start to figure out, so that's why the first thing is commutativity, is because that cuts what we have to memorize almost in half, right? And then the next thing is adding 0. Well, that makes sense. This is simple as hell, right? And of course, this will be the same thing that way. That's why we don't worry about it at the moment. So that's a major thing, add 0. That's our idea of what? Adding 0 stays the same as the idea of identity. I love it. Kick ass. Let me see. Oh, the next thing we could do is to count on by 1 or 2. So something like 1 plus 2. So before they start doing this, what have they definitely learned related to this? Before you start talking about addition, what do they know going in? I mean, what would you need to know to even be able to tell what the hell this means? What would you have to be able to do as a student before you start talking about adding these numbers?
Know the numbers?
Know the numbers and be able to count them off, yes? Okay, that was a weird question, I know. You're all like, I don't know, man, how to tie your shoes?
It's like when you get in the car. You'll be
Yeah. So to get the 1 in the 2 column, it's pretty simple for students to go 1 plus 1 with a 1, 2. It's 2 because it's 1 step away. So it's reinforcing that measurement model, the movement going on. And this is, I don't know if you guys are picking up on, and I've said this before, but you guys don't even think that way anymore because you've got so many things memorized and all that kind of stuff. But when they're first working with it, that's why it's so important. You got the physical model, the set model, where they can play with stuff, and then you got the movement model. Together, that gives them a complete picture because they're not always going to have stuff to hold. They have to understand numbers absent physical objects, right? So that's counting by 1 and 2. I'm going to move this down. So you start to fill this. So now we can fill in this and this, because you add 2, it's 2, 3, 4. But you don't want them to say, now add 7, so add 7 to 2. All right, let me count by 7. No, right? You don't want to start to say that's the way it's done, because that'll suck for them later in life. Add 81. Okay, I'll be a minute. All right, I'm still 81's a little fun. Right? You want them to start learning other ways. So the next thing we could do is something that already happened, is I can identify anything in here that makes a nice whole 10, right? Mm-hmm. So they can start looking for, and in fact, where are those places located? So like, it'd be 1 plus 9, of course, but let's start down here. 9 plus 1, 8 plus 2, 7 plus 3. So do you see how the 10s are just going to go, right? Okay, I like it. You guys with me? And that, of course, makes sense because it's one of the first strategies to add a series of numbers together, and it's beautiful that it happened earlier. You look for what makes a round number because then everything else is a little bit easier. Okay. You got it right here, Jeff. Oh. Well, I should have asked you guys, well, I don't know, this would be a little evil, just to ask you what else do you think we could use, because it's like wide open, but you can then start doing stuff like 4 plus 4, the idea of doubling, right? And to be really honest with you, I'm not really sure where counting by multiples shows up in the curriculum in elementary school, but you know, in like 3, 6, 9, it should be not immediately after learning how to count, of course. In fact, probably, I don't know when exactly after that, but you start counting by multiples pretty soon after. So looking for 4 plus 4, 3 plus 3, 2 plus 2, that's just their doubles. That kind of makes sense to be the next sort of strategy to use. I like it. And then, of course, now we start to leave this thing a little bit, but, well, this is kind of a silly one for right now. I'm going to bring it up in a minute. This one's kind of silly for this. Yeah, the last several are kind of silly. Okay, 11. So let me show you. Here's the 10 thing we talked about, the diagonal of 10. Then you start to fill in, get over here, the doubles. Right, the doubles. And I don't know if they have a complete one. No, of course they don't. They want to screw us up. Okay. But the last few options are adding 10. Adding 10 is pretty simple. I don't know if this is not going to work. So the last few options are adding 10. So like if I had 7, how do I add 10? 17, right? So the naming system we use, even though we pointed out before, it's not really consistent. It's not 1T7.
Yeah.
It still tells you what the answer. 10 plus 7 is 17. 7 and 10. Hey, that's good. So adding 10, of course, is easy. Should be.
Yeah.
What was the other one, Jeff? Associativity is a little bit interesting. Oh, associativity. Okay, here's how associativity helps. You okay? Yeah. So if I had something like 9 plus 6, and I think this is partially why people don't. Now listen, I don't like everything about Common Core, but it does get some shit it doesn't deserve, and it's just because we use numbers all the time. We don't think like this, but people that have never used numbers need several ways to think about them, right? So, one way to do this is to say that this is 9 plus 5 plus 1, right? And then, of course, right? And then, of course, you get the 10 plus 5. Okay, all right. I like it, yes, maybe. Okay, I like it. And of course, real quick, just a little, because this is, got to make it more difficult. If we had base 8, we try to see things that make 8. Let me throw this at you. So what if I had 3 base 8 plus 7 base 8? No.
It'd be 12.
So what makes 8? What if it was 3 base 8 plus 5 base 8? What's that?
That'd be
That would be 8, but how do you write 8 in base 8?
10.
1, 0. And I really want you to see what was 9 plus 1? 1, 0. Because it hit the base. So what is 3 plus 5 base 8? 1, 0 base 8, because it hit the base. Right? So how would I do 3 base 8 plus 7 base 8? Well, I do 3 base 8 plus 5 base 8 plus 2 base 8. Yes? And then 3 base 8 plus 5 base 8 plus 2 base 8. 3 base 8 plus 5 base 8 is 1, 0 base 8 plus 2 base 8 is 1, 2. Yes? Maybe? Weird shit. We're not used to thinking that way. Sort of like going to Canada and looking at your speedometer and freaking out for a second. No, so because they use kilometers. But it makes sense, but it's not like immediate sense. You don't have to think about this shit right here. You don't have to think about that. But there you better think about it because we're in a different base. But it's the same exact idea. What do I combine to hit the base? Because then everything else is on top of that. Maybe. Okay. Let's see. Oh. So let me show you. I think this is a good time. Yeah, that's a good time. Let's do it. Let's look at some cute little people trying to figure shit out. I don't know. I don't think I can record that.